All right, so let's get started, guys. So first of all, let me see. All right. So first of all, one update on the labs. Uh, so as you know that this week we will be covering the most of our discussions on diodes. So we haven't covered a lot on diodes. So what we are going to do is that for the labs, we are going to spend this week as well as on the next week on lab number 3, which means that if you have your lab this week, you can either choose to do it this week or the next week. Okay. If you have already finished it, that's great. If you haven't, you can choose to do it this week or next week. And if you were not able to, let's say, finish any of, let's say, lab 1, lab 2, or lab 3, so this will be a makeup opportunity that next week you can go to the lab, finish whatever you could not do in the earlier lab sections, and then just make up for it. So that's an opportunity for you if you have not completed all the labs till now. So that's what we'll be doing this week and the next week. And today we are going to continue our discussions on diodes. Any questions on the labs? I saw that there were a few questions on the GroupMe chat. Yeah. Then you don't need to. Then you don't need to. So if you have all the labs finished till now, you don't need to go to lab next week. Okay, I'll inform the EPIs about that as well. But that's a good question. But if you haven't finished, if you want to make up for some of the earlier labs, please use these 2 weeks to do so. All right. So in terms of diodes, what we had discussed earlier, yeah, more questions. Homework is also to Friday because just to accommodate for a few students who had requested that, okay, we needed a little bit more time. So you can submit the homework number 3 till Friday as well. Okay. And because again, homework number 4 will contain mostly diodes and MOSFETs. And since we need a little bit more time to cover that, we are pushing homework 3 a little bit, and that's fine. Okay. But if you have already submitted your homework 3, that's great because you don't need to do it again. All right. Now, in terms of diodes, what we had discussed earlier was, maybe I can have both the screens down. Right. So what we had discussed earlier is that there should be P-type semiconductors, there could be N-type semiconductors, right? So you could have a P-type device or an N-type device. What does a P-type device mean? That it has excess of holes. What does N-type devices mean? They have excess of electrons. So if you dope your pure semiconductor, which could be silicon, germanium, gallium arsenide, if you're doping it with N-type impurity, which has additional electrons, for example, you could dope it with phosphorus, which has one additional electron than silicon. Silicon is in group 4 in your periodic table. If you add any of the material from group 5, that will have one additional electron, right? So I hope all of you are very familiar with the periodic table. And now if you're adding an impurity from group 3, let's say boron. Boron has 3 electrons on its outer shell as compared to 4 for silicon. So it has one less electron. One less electron means one additional hole. So absence of an electron is presence of a hole. So that's how we interpret semiconductors and the impurity in semiconductors. So P-type semiconductor means you have one less electron. N-type semiconductor means you have one additional electron. And it's not only one, it could be multiple throughout that semiconductor, but it's just that if you have one impure ion, so let's say if you have a phosphorus atom inside your silicon, that will result in one additional electron. Similarly, if you have a boron atom, it will result in one less electron. And we have looked into what happens if you put the P-type semiconductor and the N-type semiconductor together. There's always a depletion region that forms at the junction. And what depletion region means is that you will not have any majority carrier within that depletion region. Remember, for P-type silicon or P-type semiconductor, the majority carriers are the holes. For N-type, the majority carriers are the electrons. Now, because in the N-type region, you'll have these electrons which are free, which can move around. the ions will become positively charged, because overall, remember that we are not creating charge, we are not destroying charge. Overall, we have the same amount of charge. So that's why if you have free electrons moving around, your ions or your atoms will become positively charged. They will become positively charged ions. So that's why those positive ions plus these negative electrons, overall, they will be charged neutral. Similarly, on the p side, the negatively charged atoms and the positively charged holes, overall, they will be charged neutral. But these holes can move around. On the other hand, atoms cannot move around. If atoms had moved around, your device will be deformed. So in the depletion region, what happens is that if you have this n-type region, which has these positively charged atoms which are not moving around, they will push away the positively charged holes to the left side. Similarly, the positively charged atoms in the p-type region, they will push away the negatively charged atoms in the p-type region, they will push away the negatively charged electrons toward the right. So at the junction, you will not have any free electron or free holes which can move around. So that's why it's called depletion region. It's depleted of any kind of majority carrier. But there could be minority carriers that can flow through this depletion region, and that actually results in the leakage in a diode or any kind of semiconductor device. And that's again something that we have discussed. We have looked into forward bias and reverse bias conditions. So you know that in forward bias, or let's say first we discuss reverse bias, and in reverse bias condition, you know that the depletion region becomes wider. It becomes more wide as you are applying reverse bias voltage across the device. And that happens because the definition of reverse bias is that you will apply a negative voltage to the P side and a positive voltage to the N side. Applying a positive voltage to the N side will mean it will attract those free electrons in the N side. So electrons will flow more towards the right and your depletion region will become wider. Similarly, the negative voltage at the battery, that will attract the free holes towards the left. And that will again mean that this depletion region will become wider because the holes are moving further towards left and you get more and more negatively charged atoms near the junction. So your depletion region becomes wider and wider. The opposite happens when you have a forward bias. In forward bias, you apply the positive voltage to the P side and the negative voltage to the N side. So positive to P, negative to N. So it's very easy to remember. Now, in that case, the depletion region will shrink. It will become smaller because the positive terminal of the battery, they will also try to repel the holes. The negative terminal of the battery, they will try to repel the electrons. So electrons will, because of the existence of the battery, these electrons in the inside will try to move towards left and they will recombine with some of these positively charged atoms, which means that your depletion region will become narrower. Okay. Now, what this means is that in forward bias, so let's say this curve represents the diode current in the y-axis and the diode voltage on the x-axis. Now, toward the right side, we are applying more and more positive voltage. Toward the left side, we are applying more and more negative or reverse bias voltage. So the right side is the forward bias voltage application. The left side is reverse bias voltage. Now, as you are applying a positive voltage or a forward bias voltage, after some time, you see that there is a large amount of current flowing through the diode, which means that as you are applying that forward bias voltage, your depletion region becomes narrower and narrower. And at some point, there is a large amount of current flow through the depletion region or through the diode. The depletion region stops your current flow, right? So there are no majority carriers. There are no electrons or holes. They can flow around. They can move around inside the depletion region. So if the depletion region becomes narrower, there is more possibility that you will have flow of electrons or holes, right? And which means that after a certain point, after you have applied a certain amount of forward bias positive voltage, you'll see a large amount of current flowing through the diode as if the diode has become shorted. So it's a short circuit after application of a certain amount of forward bias voltage because you need to compensate for the effect of this depletion region. Once you have compensated for it, there can be a current flow. Okay. But on the other side, when you're applying a reverse bias voltage, you see that there is still a small amount of current flow through the diode, but it's very, very small. And that small amount of current flow through the diode happens because even in the reverse bias condition, as you're applying the positive terminal of the battery to the N side and the negative terminal of the battery to the P side, so you're trying to repel the holes from the right side toward left, right? That's what you're trying to do as you apply a positive voltage of this battery, and you're connecting it to the right side, which is connected to the N-type semiconductor. So there are minority carriers in the N-type semiconductors, and minority carriers in N-type semiconductors are holes. And these holes will exist because there is always thermal fluctuation. There is always, because of thermal fluctuations, there is always a possibility that some of the silicon atoms or any of the impure atoms, they will have an additional hole. Even on the p side, there is a possibility that some of the p side atoms will have an additional electron because of many thermal fluctuations, impurities, bonds getting created, bonds getting broken. But the possibility or the probability of those minority carriers will be very, very small. So it's usually in the range of 1 in billions and billions of atoms, you'll have one electron or one hole like that. But they are enough to create a leakage current. And that is the source of leakage current in a diode, or even later on we'll see in a MOSFET or a BJT. This is the source of the leakage current, the minority carriers. But for a diode, usually the value of the leakage current is very small, in the range of nanoamperes or picoamperes. On the other hand, the forward bias current could be microamperes to milliamperes. Now, of course, there is you can represent that in terms of equations as well, and will not prove the equation because this is part of your solid state circuit class, that how to find out what is the current that flows through a diode. And if you have taken any solid state circuit class, you'll know that the diode current equation is given as ID, that's the diode current, equal to IS. IS is called a reverse saturation current. So that's the amount of reverse current. And you will see that this is a saturated amount of current, that is a constant amount of current that flows in the reverse bias. That is your IS times e to the power Vd over eta Vt minus 1. So that's the equation for a diode. And again, the proof is given in your solid state circuit classes. So it will not be part of e-circuits because we are not discussing devices here. We'll discuss how to apply those devices in circuits. But for that, we need to know how the devices behave, of course. So from this equation, you can say that when your Vd, when your diode voltage is 0, at that time you'll have a e to the power 0 term, which is equal to 1 minus 1. So your current will become equal to 0 when you have no bias. When you have Vd equal to 0, your current is also equal to 0. So it is this point that your voltage is 0 across the diode, the current through the diode is also 0. There is not even a leakage current because, of course, without voltage, you cannot create current. When your ID, when you are in reverse bias, that is your Vd is much lower than 0. So you put a value of Vd which is much lower than 0. So this e to the power negative exponential term, that would be very, very small. So a very small value minus 1, that will be almost equal to minus 1. So that's why ID equal to almost minus Is when your Vd is less than 0. And when your Vd is more than 0, when you have a forward bias condition, in that case, your ID will exponentially increase with your Vd. Of course, that's an approximation because always there is this minus 1 term. So it will not be fully following the exponential curve, but you'll see that it's almost equal to the exponential curve because e to the power, let's say 10, is such a large number that e to the power 10 minus 1 is almost equal to e to the power 10. Okay, now two other questions that may remain, that what is this eta and what is Vt? So Vt is called a thermal voltage and it is defined as KT over Q. Again, the why Vt is there, that question will be answered in your device physics classes. But Vt is called the thermal voltage, which is the equivalent of the energy that is present at a particular temperature divided by the charge of an electron. So you know that energy divided by charge, that gives you a voltage. So this is the equivalent of the energy present for any electron. That's your KT term. That divided by the charge of the electron gives you thermal voltage, which is the equivalent voltage corresponding to a particular temperature at which you are trying to calculate the energy of the electron, and dividing that energy of the electron by charge, you get the equivalent voltage, which is called a thermal voltage. So there is no physical existence of this voltage, but this is something that we mathematically represent to sort of represent the temperature at which you are trying to calculate everything for the electron. So if your T is equal to 300, that is room temperature, and K is called the Boltzmann constant. So Boltzmann constant is 1.38 times 10 to the power minus 23. That divided by the charge of the electron gives you the thermal voltage, value of the thermal voltage. And if you calculate that, it comes out to be about 26 millivolts. Eta is called a non-ideality constant. So it's an empirical number. It's something that is found through experiments and not from theory. Theory will say, like if you again go back to your device physics, your theory will say that this should have been e to the power Vd divided by Vt. So in theory, there is no existence of this eta term, eta factor. Of course, you can have more complex theory and include it, but in a simplest form of the theory, you'll see that it's generally Vd divided by Vt. But this eta factor is an empirical non-ideality constant, which is usually in the range of 1 to 1.3 for a silicon diode. And it's generally technology dependent. So it's dependent on the technology for, let's say if you're using a 180 nanometer technology, that means the length of the devices are 180 nanometer, then it can have a different non-ideality factor. If you're using a separate technology node, you know, for example, Intel has been working on sub 10 nanometer nodes. That means the length of the devices are less than 10 nanometer. So we'll go into those details later on in the class as well. But that's what technology means, that what are the dimensions of the devices that you are using for a particular technology. And depending on what are the dimensions of the devices, this non-ideality constant can change. And usually it's in the range of 1 to 1.3. Okay, we have already defined what are our majority carriers and minority carriers. So majority carriers for N-type material are electrons. For P-type material, these are holes. Minority carriers, it will be just the opposite. For N-type material, minority carriers will be the holes. And for P-type material, the minority carriers will be the electrons. Now, there is something interesting that happens as you keep applying larger and larger negative voltages or larger and larger reverse bias voltages. And this was something that was studied by an American physicist, Clarence Zener. And according to his name, this region is called the Zener region. What it really means is that as you are applying more and more reverse bias voltage, at some point, you'll see that the device breaks down. And this is something you might have seen in the lab, that you apply a very large voltage accidentally to any device, and the device just burns out or it breaks down. So in this case, what is interesting is that as you are applying this voltage, it breaks down. What it means is that you'll suddenly see a large amount of current flow even in the reverse bias region. But the funny thing or the interesting thing is that this is reversible. So if you reduce that voltage again, you'll start to see that the device comes back into this region once again. So it does not completely get destroyed. The device does not get destroyed, but there is a large amount of current flow through the device that is possible even in the reverse bias region. And that is called the Zener breakdown region. And again, if you have taken the device physics class, you will know that this happens because of a phenomena called avalanche breakdown. So it's like an avalanche where a small ball of ice just rolls on and it collects more and more ice, more and more snow, and then it forms a large avalanche. So that's how it works, that initially only a few electrons start flowing. They will hit other electrons, other atoms, will create more electrons, and then you'll see an avalanche of electrons. So that's why it's called an avalanche breakdown sometimes. So if you have taken the device theory class, you'll know about the actual physical phenomena. All right, usually the forward bias voltage that you need to turn the diode on, that is to conduct a large amount of current in the forward bias region, is in the range of about 1.2 volt for a gallium arsenide diode, 0.7 volt for silicon diodes, and about 0.3 volts for a germanium diode. Now, for most of the rest of the class course, we'll probably consider silicon diodes, silicon MOSFET, silicon devices. So you can consider that for all your homeworks or exams, you can consider the forward bias threshold voltage to be equal to 0.7 volts. So this is called a threshold voltage or VTH, which means that after this voltage, as you're applying the forward bias, after you have applied this much voltage, you'll suddenly see a large amount of current flowing through the diode. So this is the threshold voltage, that after this point, you'll see a large amount of current suddenly flowing through the diode. And that happens because you have made the depletion region so small that it's ineffective for all practical considerations. Okay, so there is a direct flow of current from the left side to the right side as you are applying more and more forward bias voltage. All right. Now, one thing that is interesting and we'll discuss in this class is the resistance of a diode, because again, as we have been talking about input resistance, output resistance of the op-amp, later on we'd like to go into resistances of MOSFETs, which are inside those op-amps. And that will help you understand why the op-amp had infinite input impedance and zero output impedance or very small output impedance. So to know that, it's first very important to define what do we mean by resistance. So you can have something called a DC resistance, you can have something called an AC resistance, and you can have something called an average AC resistance. So we'll define all those three terms. But for rest of the course, we'll mostly focus on this AC dynamic resistance. So that will be something that whenever people talk about, let's say, resistance of a circuit, let's say they give you a MOSFET-based circuit and ask you to find out the output resistance. So generally, they are asking about this AC dynamic resistance. They are not asking about the DC resistance or what happens when you apply a DC voltage and see a DC current through it. So they are asking about what happens in terms of an AC. Now, the DC or the static resistance is defined as whatever you already know about resistances. So it's a ratio of voltage over current. So even for the diode, if you consider any point in its operation, and you know that there is a particular amount of voltage that you're applying at this point, and then you get a particular amount of current, right? So this is the ID-VD characteristic of the diode, which we had defined earlier. So the resistance is basically a ratio of that voltage to the current. The AC or the dynamic resistance is defined as a small change on this line. So this is the ID-VD characteristic of the diode. So on this characteristics, if you have a small amount of change in VD, you'll have a small amount of change in ID, right? And that's what AC is defined as. So if you have a sine wave, so you're trying to, your originally, let's say the voltage was here. You're trying to create a small amount of change in the voltage, right? That's what you're doing with the sine wave or any kind of AC signal, that you change something. The definition of AC is that it is changing. So if you have a small amount of change in the voltage, you'll have a small amount of change in the current. And the ratio of that small change in voltage over the small change in current is defined as the AC resistance. So the AC resistance, which I'm writing as a lowercase RD. So remember, in the previous case, it was the uppercase RD, which generally represents that, okay, this is a DC quantity. The lowercase RD will generally represent that it is an AC quantity. And that lowercase ID is del VD over del ID, a small change in the VD over a small change in the ID. So as you know that even though we are defining as a ratio of differentials, it's basically a derivative, almost approximately it's a derivative of VD with respect to ID, right? So if you go back to your ID equal to IS times e to the power VD divided by eta VT minus 1, this equation, and you can, let's say you're just considering it for forward bias condition, which means you have a large VD. So you can ignore this minus 1 term. So this equation becomes ID almost equal to IS times e to the power VD divided by eta VT. You're ignoring that minus 1 because you're in forward bias, your VD is large, and that's why your exponential term is much, much larger than 1. Now, if you take a differential of this equation now, so if you calculate the del ID over del VD, or if you calculate the derivative of ID over VD, you'll end up with this equation that the derivative is equal to IS times e to the power VD over eta VT times 1 over eta VT. Now, IS times e to the power VD over eta VT, that's nothing but your ID. So this entire derivative becomes ID divided by eta VT. Now, remember that this derivative is the derivative of ID with respect to VD. If you want to calculate the resistance, you need to calculate the derivative of VD with respect to ID. So you just need to calculate the opposite, the reverse of this. So RD is defined as del VD over del ID. And here what you have found out is del ID over del VD. So what did you do? You'll just take 1 upon this entire right-hand side, and that will give you the value of your AC small signal resistance, and that becomes eta times Vt divided by Id. Now, if you consider eta to be equal to 1, that's true for most of the scaled silicon technologies, and your Vt is already 26 millivolt. So your Rd can be defined as 26 millivolt divided by Id. Now, of course, there is one additional term you see here in this equation. And what is that additional term? That additional term is basically the contact resistances. So whenever you have the diode, so let's go back to one of the earlier pictures that okay, I have my diode over here. I have my battery over here. But as I am connecting the diode and the battery with these wires, the wires will have some additional resistance. The contact itself will have some additional resistance. So usually those additional parasitic resistances also need to be considered if you are trying to be more accurate. So that additional term, along with this 26 millivolt divided by Id that you already saw here, that additional term represents those parasitic additional resistances that may come because of the contact, because of the wires, because of any other non-ideality in the system. But overall, that will be very, very small. It's usually in the range of 0.1 to maybe 1 or 2 ohms. On the other hand, this 26 millivolt over Id, if your Id is small enough, let's say Id is in microamperes, then you know this resistance is already in kilo ohms. So kilo ohm plus 0.1 ohm does not mean much, right? So it's almost same as this 26 millivolt over Id. But I just wanted to mention RB as well, just so that you know that this exists. But in most cases, it can be ignored. In the reverse bias region, if you do the same calculation, you will see that your RD will be almost equal to infinite. So it will be very, very large. And the diode acts like an open in reverse bias. You can also define average AC resistance, that you can take 2 points in the diode characteristic. Let's say you take this as 0.1 and you take this as 0.2. Now, this is something like calculating the slope, which you have done in high school for any line, that you have a delta difference of those 2 points in terms of VD, and the delta, that is the difference of those 2 points in terms of ID. So the ratio of the y-axis value divided by the ratio of the difference of the x-axis value, that would be your del ID over del VD. If you want to find out your resistance, then you need to find out your del VD over del ID. So this is called a point-to-point resistance, that you define 2 points on the curve, and the difference of voltage divided by the difference of current for those 2 points, it's same as calculating the slope of a line, as you have done in high school. And that gives you the average AC resistance. But for most of we'll mostly be considering the dynamic AC resistance for most of our discussions later in the course. Yeah. And also whenever you take any future circuit design course, by resistance, most of the times they will mean the AC dynamic resistance. So what is your diode's equivalent circuit then? We know that the diode acts as a short when it is forward bias, that it lets a large amount of current flow through it, and it acts as an open in reverse bias, that it does not let current flow through it. Even though there is a small amount of leakage, but if you ignore the leakage, in reverse bias, you have an open circuit. So the equivalent circuit for the diode in forward bias is basically this, that if you consider an ideal diode, that okay, it lets current pass, it's an ideal short circuit in forward bias, an ideal open circuit in reverse bias. But along with that, you will have an AC resistance or an average resistance associated with it when you are in forward bias. And you have some forward bias threshold voltage, that only after you apply this much amount of voltage, the diode will actually start conducting current, right? So this is called the threshold voltage of the diode. Sometimes some books will also call it knee voltage. Why is it called a knee voltage? Because this is the curve, how it looks like, right? So, and we are defining the threshold voltage as the point, even though remember that it may not be one particular point that is defined as threshold voltage. It's probably, it could be this point or the point that is just beside that or the point just on the left-hand side of that. You can define your own. For most practical uses, there is also a very strict definition of the threshold voltage that you'll study in graduate classes or when you discuss MOSFETs, we'll discuss about a little bit about the strict definition of the threshold voltage. Right now, the loose definition of the threshold voltage is that whenever the current starts increasing significantly compared to the small value of the current on the left hand side, that point will be defined as your threshold voltage. Why is it called a knee voltage, or it's basically KNEE? So it looks like a knee of a person, right? So as the knee is bent. So that's why it's sometimes called a knee voltage as well. So the VK actually defines your V knee. It can also be termed as VTH to represent that it's a threshold voltage. Okay, diode capacitance. Now, of course, why would there be a capacitance in a diode? Because, you know, again, go back to the figures that we have for forward bias and reverse bias. So let's say if we have this figure, what we have here is a conductive plate on the left-hand side. You have a conductive plate on the right-hand side. In the middle, what do you have? Near the junction, you have a depletion region. And remember, depletion region is somewhat like an insulator. This is something we discussed in the previous class, that it's kind of like wood, which does not allow current to go through the junction. So you have an insulator in between and two conductive plates on two sides, right? So that forms a capacitor, that you have two conductive plates on two sides and you have an insulator in between. That is the definition of a capacitor. So the diode can also act as a capacitor, both in the forward bias and the reverse bias region. Now, what would be the value of the capacitance? Again, going back to high school physics, capacitance is epsilon times A over D, where you know about epsilon, which is the permittivity of the material. You know about A, which is the area, the common area of the two plates that you are considering for the capacitance, and D is the distance between them. Now, what is the distance? What is the dimension of the insulator here? If you are in the reverse bias or forward bias region, the depletion region is your insulator. So if your depletion region is the insulator, the width of the depletion region, that's basically your D in this capacitance. So in reverse bias region, as your depletion region is wider, D is more, D is larger, which means the value of the capacitance will be smaller in reverse bias. In forward bias, the depletion region will be narrower. And if the depletion region is narrower, D will be small, which means your capacitance will be larger. And that's what you see in this particular plot later on. That in forward bias, because your plates are close by, your depletion region is narrower, so your plates are close by, your capacitance is higher. In reverse bias region, the plates are much further apart. And that's why your capacitance is smaller. So you can use the diode as a capacitor as well. And sometimes you'll see that it's basically a voltage dependent capacitor. So some of you might know about varactors or variable capacitors. And variable capacitors are very useful in many electronic circuit designs, specifically oscillators, or when you are trying to design a tunable circuit, tunable filter or a tunable oscillator, where you need tunable values of a capacitance. And as you see that here, the value of the capacitance is a function of the voltage that you apply across the diode. So this is called a variable capacitor or a varactor. Question.
So AC supplies sort of out of phase.
AC supplies can get out of phase because of the capacity. What do you mean by that?
Because there are
so of course, capacitance will have some amount of phase difference. So is that what you are meaning by out of phase? Yeah. Whenever you have a capacitance, you can have some amount of phase difference for a AC signal. So the two sides of a diode may not have the same AC phase. There could be a small difference in the AC phase because of the capacitance, if we are referring to that. But yeah, that's too much of an advanced concept, so we'll not get into that right now. All right. So again, I'll just skip through some of these slides because this just talks about the diode symbols, packaging, testing. So you can look into these slides yourself, which does not talk about a lot of technical details. We have already talked about Zener diodes, which is a diode that is operated in a reverse bias region. And common Zener diode voltages are about 1.8 volt to 200 volts. So that's the Zener breakdown voltage for most of the common Zener diodes. You can also have probably some of you already know about LEDs. So these are basically light emitting diodes, and they emit photons when they are forward biased. And these photons could be in the infrared region or visible spectrum. And for their case, the forward bias voltage is usually in the range of 2 volts to about 3 volts. You can also have arrays of diodes. So for example, the IC that you have bought for your lab that already contains multiple diodes, right? Or is it the single diode one that you have bought? Maybe some of you who have already done the lab can tell me better. But yeah, you can also buy arrays of diodes or arrays of LEDs, which you can use for multiple applications. The next thing we wanted to discuss was, if this diode is there in a practical circuit, how would you analyze it? How do you solve a circuit when you see there is a diode in it? So of course, we'll start the discussion, but maybe since we have only 10 minutes left, we'll continue our discussion in Friday's lecture as well. But I wanted to start the discussions a little bit because it may help some of you in the labs as well. Okay, so the first thing that generally, and again, from your circuits one, you may know about load line based analysis, which basically says that if you have multiple different components in the circuit, what you can do is that you can just draw the characteristic of each one of those components separately, and then and then let's say, for example, here you see there are two different characteristics that are drawn. The one that is drawn in blue, that is basically the characteristic of the diode in forward bias. What is drawn as this slanted line, that's basically the characteristic of a resistance. That I have a resistance, and if my voltage, it's not basically the resistance. Let me show you the actual circuit, then it will be clearer. Let's say this is the circuit that we are trying to analyze. That you have a battery or a voltage source, you have a diode, and you have a resistor. Okay. So what is happening here? That as I apply a positive voltage here, this battery will try to create a current in this direction. Now, of course, this PN junction diode, so this is the P side and this is the N side. That's how the PN junction diode is defined. So as you are applying the positive voltage to the P side, this is a forward bias diode. So it will have a diode drop of, let's say, about 0.7 volts. If it is a germanium diode, it would have had a diode drop of about 0.3 volts. Now, how do we analyze this for silicon? You assume that the diode drop is 0.7 volt. Let's say we assume that there is a fixed amount of diode drop, that is the threshold voltage of the diode, that you at least need that much voltage across the diode so that it can start conducting, so that there is a current flow through it. So again, going back to the previous, that if the voltage across the diode is less than this point, there would be no current flow through the diode. So there cannot be any current flow through the circuit if there is no current flow through the diode. So only after there is a diode drop of about 0.7 volts, you'll see that there is a current flow that will start through the diode. Now, if VD is 0.7 volts, what is the voltage that is available across the resistance? Let's call it VR. VR will be E minus VD. That's the voltage that is available across the resistance. What would be the current then? The current will be VR divided by R. Whatever voltage available across the resistance divided the value of the resistance will give you the current through the resistance. And because of KCL, the current through the resistance will be same as the current through the diode and will be same as the current through the circuit. So as you see that there are two components that we have here. One is the diode, one is the resistance. Now what the load line is saying is that you draw the characteristic of the diode, and at the same time, you draw the characteristic of currents and voltages in a way that, okay, when you have zero voltage across the diode, so this is VD, so this is the voltage across the diode, and this is ID, that is the current across the diode. If you have zero voltage across the diode, you will have E divided by R, that is the amount of current flowing through the circuit. Let's say you have zero voltage across the diode, that from here to here, the voltage drop is zero. Let's just assume that, even though that's not a practical condition. Then what is the total current flowing through it? The current flowing through it will be E divided by R, because there is zero drop across the diode. So the entire voltage drop of E will happen across the resistance. So E divided by R will be the current. So that is this point. Similarly, if you assume that there is a drop of E, the entire voltage drop is happening across the diode, then there will be zero current flowing through the circuit. Right? Entire voltage drop happens across the diode. So there is zero voltage drop across the resistance. If there is zero voltage drop across the resistance, that means there is zero current across the resistance as well as the diode. So this point says that there is the entire voltage drop happens across the diode, and that's why you have zero current through the circuit. Now, as you connect these two lines together, that's basically the resistance of the circuit. And the crossover point of the diode characteristic and this load line will give you the actual solution. Question?
So both of those points, the E over R and E by itself, are...
They may not be practical.
Yeah, like
but
in real world.
In a real world, only this point exists. None of the other points exist. So you are trying to find out what is the real world point. What is the real? So this is also called the Q point or the quiescent point for the diode, or the operating point of the diode. So that's the only real world point that you have here. None of the other points on the load line are real. So there cannot be any scenario that the diode drop is zero. There cannot be any scenario that the diode drop is infinite or the diode drop is equal to the voltage E. But you are just doing this analysis to find out where is your real operating point is. Now, why are we doing this? Because if your E point changes, if this E value changes, let's say you apply a smaller battery, instead of a 5-volt battery, let's say you have a 1-volt battery now. So your point E will shift towards left. And the point E over R, that will shift towards down, bottom. So you'll have your load line. Yeah, I did not draw a line, but if I had drawn a good looking line over here, let me try. Yeah, probably something like that. Then this will be your Q point or the operating point. So what you're trying to do is just to find out what is the operating point at which your diode as well as the other part of the circuit is operating at. So this is from a graphical representation, and this is just doing the mathematical calculation. You're doing the same thing, but here you are doing the mathematical calculation based on KVL and KCL, and here you are just trying to find it out graphically. All right. So now what could be the defined diode configuration? So let's say you are applying the diode in a reverse bias. So you have your positive terminal of the battery here and the negative terminal of the battery here, but you have applied the diode in a reverse bias. So this is your P side and this is your N side. So as you see that the positive terminal of the battery is connected to the N terminal of the diode, and the negative terminal of the battery through the resistance is connected to the P terminal of the diode. So this is reverse bias. Now, if it is reverse bias, the diode will ideally be an open circuit, which means all the voltage drop will happen across the diode. So the diode voltage will be equal to E. The voltage across the resistance will be equal to 0, and the current across the resistance as well as the current across the diode will be equal to 0, assuming that there is no leakage current, of course. Okay. So that is your reverse bias, and this is just a series configuration example. The previous one was also series configuration, but the diode was forward bias. So I looked into the two scenarios when the diode is forward bias and when the diode is reverse bias. How do you sort of mathematically analyze this? And the reverse bias is probably the easiest one to analyze because the entire voltage drop happens across the diode, because the diode acts as an open circuit and there is no current flow through the circuit. You can also have parallel configuration of the diodes. So we'll probably stop after this slide. But what parallel configuration means is that, let's say you have this battery over here, you have a 0.33 kilo ohm resistance, and then you have two diodes, D1 and D2, connected in this direction. So this is P side, this is N side. And the diode drop in both cases is equal to 0.7 volt for both the diodes. So VD1 equal to VD2 is equal to 0.7 volt. And this is your output. The drop across the, let's say one of the diode is again your output. So because this is parallel, it's the voltage drop across the diode that you are taking in as your output voltage. So your output voltage is equal to 0.7 volt. So the drop across this resistance is the rest of the voltage. if your battery was a 10-volt battery, the rest of the voltage will be 9.3 volt. That will be the drop across the resistance. So what would be the current flowing across the resistance? That would be the drop across the resistance, which is 9.3 volt, 9.3 volts, divided by the value of the resistance, which is 0.33 kilo ohms. So the current across the resistance will be 28 milliampere. So whatever is flowing in this direction is 28 milliampere. Now, because these are two parallel diodes, the current will be divided across the two diodes. And remember that these diodes are forward biased. So they can conduct current. And they are conducting current because V0, the drop across the diode, we are assuming to be 0.7 volts. So they can conduct current. Now, because there are two diodes in parallel, the current of 28 milliampere will be divided into two parts. And assuming that both these diodes are identical, there would be 14 milliampere current flowing through each of the diodes. Because they are in parallel, so the current will be divided, and current will be divided equally because we are assuming that the diodes are identical. So you'll see a 14 milliampere current flowing through each of the diodes in this particular parallel configuration. So we'll stop here and we'll continue in the next lecture with half-wave rectification and other application of diodes.
In the case that the two diodes are not equal, then the resistance, like
then you have to think about the AC resistance of the diode, So they can have different resistance, and then there could be different.
you can do something like parallel.
Yeah, that's the parallel. The previous case.
Like a parallel calculation, like.
Yeah. So how does the diode look like? The diode. Sorry. The diode look like this, right? So it's a resistance followed by an ideal diode. Ideal diode means just a switch on or off. So you have a resistance, you have a voltage drop of 0.7 volts, right? So the 0.7 volt only means that right now the diode was in forward bias in a previous case. Now what you're saying, if the diodes are not identical, this resistance will be different. So those two resistances will come in parallel, and that will determine how much current will be flowing through each of the resistances.
Yeah, I think it will be also count.
This can also be different. Yes. So
like for example, 0.3 and other 0.7, then
it makes it interesting that if one is 0.3 and one is 0.7. So
then for example, that would mean like this one get a different you get a different kind of voltage.
So that will make things very interesting and very much complicated. What will happen in that case is that if you are making sure that you want to have both the diodes in forward bias, you have to consider the 0.7 volt drop across that both the diodes will have 0.7 volt drop, which means that for one of the diodes it will be in this region where it's just crossing the threshold. For the other diode, we have 0.7 volt threshold voltage. For it, or 0.3 volt threshold voltage. For that, it will probably be somewhere over here. So it will try to conduct more amount of current. And that will be evident because for that diode, you will see that it will match up with the calculation in that way. That this resistance will be such that Q point will be somewhere over here, and the resistance for the other diode will be such that the Q point will be somewhere over here. So that's how it will look when you actually put two different diodes in parallel. But yeah, generally you won't do that unless you're just playing around with different components. Generally, you try to keep like identical or almost identical devices.
That's gonna make it that complicated.
Yeah, but that's a good point. It's a thought process, right? It's a thought experiment, and that's good that you're thinking about it. Hey,
yes. Well, I was wondering, I'm not sure how you get to
the DC point of the output. Okay, so as you see, so for example, the minus is clear, right? If this is 5 volt because of the virtual ground property, you have this at 5 volt as well. Now, generally the op amps are designed in a way that if you are connecting them in feedback, so for example, if you are connecting this one and this one together, if the DC voltages are different, it will create a DC current flow through the op amp, right? And like I know where you're going, but if there is a DC difference between these 2 points, there will be a DC current, and that is not now that will not probably understand that because we haven't discussed what's there inside the op-amp. But usually the op-amp is designed in a way that if you push this point and this point, there will not be a DC current flow from here to here, which means that DC point can happen. If there is a DC current flow, it's a wastage. There is a current flow through the device and you are not doing anything with that current. It's a wasted amount of current, and that's why op-amp designers will try to avoid that.
But I'm just wondering because this
oh, the output resistance is zero in an AC system, not in a DC system. Right, the AC output resistance is zero. The linear equivalent model, that's an AC equivalent model.
Okay. I don't know. So we're going to
yeah. So for now, yeah, you can assume it to be true. Why it is true, we'll discuss that later in the code, and I'll come back to it. I remember that I want to mention that why this point and this point the DC potential will be zero. So once you discuss the internal circuitry of the op-amp, I'll probably again come back to this particular example from homework number 2 or homework number 3 and show why these two DC points were equal to or equal.
Okay. And also, question. So, oh, that's because
I don't think it was here. This is the concept. Like if your offset is 2 millivolts and if your gain is 1000, because of that offset, your DC point will be shifted by 2 millivolt times the gain.
oh, okay. Okay, that makes sense. Thank you.
So I basically like modeled it after the homework 3 like traditional problems. So I picked C1. And so I got these messages to look like now. Why is it like I know that one is main one is like a variable, but why is it that you
Yeah. You can take 10, you can take any other value of the log. It's just that you want to make that value as far away as we can. But what this does is that it reaches other post factor. So you can, what you're doing is that you're bringing it 10 times away from the primary source or the dominant.
Okay, but then wouldn't that feel like if our filter is like this, right? And we're placing have a pole here.
Yeah, your filter will look a little interesting.